IEEE section. We've just started our new calendar year in terms of the board officers positions and that kind of thing. In fact, I think my first official day is actually tomorrow, February 1st. So today is Dave Paulson's last day. Dave's been the chair for I think 6 years, so we owe him a great big bunch of thanks for everything he's done, and he's always done such a great job of corralling this group and getting everything organized, and I'm hoping I can do half as well with some of that. I have been chair before in the past. It's probably been about 7 or 8 years ago when I last did it for a year or two, but it's changed immensely, as you can imagine, in terms of the people that are involved with it. And then obviously post-COVID here, or we're now in this hybrid mode of distance presentations and also in-person stuff. And so just a bunch of changes going on, but I just want to thank everybody that's been involved and everybody that's continued to participate through the last couple of years with COVID. So tonight we have an exciting speaker from the local Rochester area, Brandon Schenck. He's been around Rochester for a long time. He's worked for IBM. He's currently at Marvell. He's worked for Avera Semi and Global Foundries. And so he can talk more about some of his positions, but just know that, you know, he's led a lot of technical efforts to build first in technology designs for ASICs, and he's used that experience to lead new complex customer designs in 5 nanometer and 3 nanometer lately. Very strong background in technical leadership in all aspects of ASICs and semi-custom large-scale designs, including RTL, simulation, design for test, physical synthesis, clocking, PD, etc. And so very excited to have Brandon here tonight. Thanks to Chuck and the other Marvell folks for being willing to participate and provide this information. So with that, I'd like to introduce Brandon, and once he's through his presentation, hopefully we'll have some time at the end for questions. But I think, Brandon, you would probably accept some questions along the way too, I'd assume.
Yeah, accept, encourage, absolutely. This is a dynamic conversation as far as I'm concerned. So if you have them, ask them, feel free to interrupt me. I'm not always watching for the hands. So yeah, that's just fine. And thanks for that introduction, Paul.
All right, go ahead and take it away, Brandon. Thank you.
Yeah, so just to preface, these are some slides that we share internally with our new hire groups, and they've been used in our industry day to just kind of talk about where Marvell specifically is focused and really what we're doing as part of the industry. I want to lead off by saying that they do have a little bit of a Marvell bent, but the intent here is not to advertise Marvell. It's to talk about what we're doing in the infrastructure space, in the industry, and certainly what the rest of the industry and our customers are seeing and asking for. So sort of with that is the focus, I can dive in here. It's really talking about the trends of where cloud optimized custom silicon is going. And I'll talk about that, right? It's more than just a software play. You know, for a long time, I think hardware guys have thought the cloud is somewhere where software has been playing. But clearly that's not the case anymore. And our customers are recognizing that in spades and moving much more to customized silicon to enable their cloud applications. Across multiple nodes, you know, we'll see this allows us to sort of follow the trends on where the best vantage point for customer modularity and growth is. So really, this is all about infrastructure, right? We're talking about customers who are deep into infrastructure and what that really means, right? It's data. It's processing data, whether it's with embedded CPUs or other you know, complex logic on an SoC. It's moving data. This is networking, NICs, both smart and dumb NICs, routers, switches, storing of data, interfaces like high bandwidth memory, HBM, DDR, you know, on package DDR, LPDDR, things like that. And then security, right? Securing data through custom security IP, things like MACsec, one-time programmable tokens, and security keys. Two, infrastructure has always been modular, and this is really the takeaway from this. I'll cover it at the end, but modularity is everything right now in silicon. Think about customization, right? Rivers that need a bridge, for instance, are not all built the same. A road can carry thousands of cars per hour in, say, Shenzhen. That's very different than a road that would carry bikes in Amsterdam. They all do the same thing. They move people and belongings around, but they have very different design points and very different optimizations. In semiconductors, it's no different. We're investing now to develop in advanced nodes, things that exceed the cost of major construction projects. And I think a lot of people who are in silicon recognize that. The same level of modularity.
That's awesome.
Say again. Oh, Brian Words, hey buddy.
I think
that.
somebody just called your presentation awesome, which is good.
Yeah, thanks, Brian. I appreciate it. Yeah, so the same level of modularity that became standard in the community infrastructure is now essential for the silicon industry. So it's all about making data infrastructure modular, and I know I keep saying that, but in the industry, right, building unprecedented platforms for technologies, things that are proven and innovations needed are things like design flows in the most advanced technology nodes. And a lot of us are familiar with that. A lot of us that have worked in silicon for a while have spent a lot of time and effort on creating modular design flows. But we go beyond that. We go into advanced IP, latest high performance interface, data rates at lowest power, things like that. And clearly what we've seen with acquisitions and consolidation in the market is a significant increase in the scale of those investments in advanced packaging techniques, right? So it's building up, it's scaling out rather than just focusing on, monolithic silicon. There's really few in the industry that are tackling this. And it's clear from, like I said at the top, customers pushing back on this, that this is really how we're going to advance into the next age of silicon. We understand that these problems are really talking, not about challenges, but about opportunities. Our customers are really sophisticated, and I imagine anybody that works with customers in silicon can say the same. They know the details and the problems that they need to solve, and in many cases they've studied them carefully with teams of engineers, and they know exactly the data points they need to be at. They have incredible insights in those problems, and they want to partner with someone who's advanced in technology and the know-how to solve those problems. Those customers may buy tons of standard products wherever they can. And we've seen that. We've seen customers go buy, millions of units of NICs or NOCs or other things that they can pull off the shelf. But now they're finding that there's some cases where general purpose products just don't meet the requirements in the most optimized fashion. And it's all about squeezing out that optimization. So customization is really the key to truly answering those needs.
So on optimization, Brandon, are you talking about performance or cost?
Yes, both. And it's interesting, but I'll make a point here in a moment that you can get both, right? And in fact, starting to deconstruct the SoC model, deconstruct sort of the classic monolithic model, even though it results in more silicon area, potentially, that is more silicon, as a solution, you actually save on quite a bit of cost and your performance goes up. Let's take a test. How many of us have seen this? The number of transistors on an integrated circuit will double every 18 months, right? We know who said that? Anybody? This one's easy. Gordon Moore, right? Yeah, that's right. Well, Gordon Moore, I'm going to be a little careful here, but Gordon Moore maybe was slightly incorrect. What gives me the right and the ability to say that? Well, if you're looking at a piece of silicon and technology, maybe Mr. Moore was pretty close. But what we're seeing and what the industry is starting to trend to is the number of transistors in an integrated solution, right? If we don't focus so much on the circuit, we'll double not 18 months, but every 12 months, right? We're really seeing acceleration in the integration. Consider an AI training solution in 7 nanometer, right? Let's just, piece it down. If you have one logic die, and let's say we have 2 memory die and a baseline transistor count, we're seeing that in 2 years we can map that into a 5 nanometer solution and just about or more than quadruple across the board the play, right? The number of logic design. We're now fitting 2 instead of 1 on, and they are 2x the size. We can go 4x, almost 8x. I should say 4x, almost 6x the density of memory, and definitely quadrupling, more than quadrupling the number of transistors with the logic shrinks we're seeing. We're also seeing explosion of custom silicon in data center, and this is an enormously emerging market. I shouldn't even say emerge. Excuse me. It's really an exploding market, right? Personalization of data center really needs diversity in the workloads and the problems they're solving. And custom solution is the only way they're getting this, even at the low end, right? Even at the lowest level NIC, we're seeing data centers across the board start to customize that silicon to get exactly the right PPA and efficiency point that they need. One, because network architectures aren't the same. Everybody wants something a little bit different in their architecture. Their workloads are definitely custom. Think large social media, search engines, the largest data centers in the world are all doing something slightly different with their data. There's performance and power benefits, and they definitely enable profit when you're scaling these as large as some of the largest data center customers are. Every penny that you're saving in PPA targeting is profit. Cloud providers know how to optimize, right? They've been doing this a long time. Like we said at the top, it seems that that's been focused on software, but it's really now mainstreaming into hardware as well. And they have the scale, right? We're building enormous data centers, and the rate at which they're going up seems to be ever expanding. It's not constant. Consider just one case, right? Product case, the tensor processor unit that Google created in 2015, kind of a single AI ML application. Over the course of 6 years, has expanded not only into its current iteration shown there on the bottom right, but also several spin-offs, right? Smaller cards that are available to you and I. NIC products, they're in GPU products, optical products, processors, etc. So the productization of things like this is just increasing tremendously. One thing we find, and I'm sure you've seen it too, is 9 out of the top 10 cloud providers are now developing custom silicon. What are some challenges for the data center? Well, copper's not keeping up, right? And we've seen certainly labs that look like this picture that we grabbed for this slide, but copper is not keeping up. Processes are expensive and they're wasteful when you have many workloads. If those aren't targeted and customized to your solution, you're wasting MIPS. And we need bigger chips that actually can be built. Right, the days of reticle size silicon, while important in certain applications, are not necessarily for everybody. Here's kind of just an example of a multi-node chiplet platform. And again, this is industry. This isn't just Marvell, but everyone's really talking about M3, right? We're still, some of our customers are still in the mindset that you got to race to be in the latest technology. And as we've seen and others have seen, is the benefits, again, right, going back to Gordon Moore, are starting to become diminishing in those nodes if you look at it just from a technology standpoint. Yet they're talking about N3. They want to be the first in technology. They want to be second to none. And they think that maybe that's their panacea. But in this specific case, N3 may not be the best fit for everybody. If we utilized high bandwidth interconnect, for instance, between die, parallel interfaces or die cut technologies, we leverage interposers for building or bridging between units. We can use chiplet and co-packaged optics or CPO to offload advanced custom IP like SerDes. And then you can use, really the latest technology for your critical functions, right? So the cases where you need the logic scale, Chuck, you were asking about performance scaling, the places where you really need the performance scaling, the power scaling, you can do that in the advanced nodes and still leverage a lot of your offload function to older technologies, which have IP available and can be readily taped out in known and trusted and qualified design nodes. This isn't just limited to wired networking, obviously, or data center, I should say. It also includes wireless networking. If we think about the need for multiple silicon here, 5G has introduced myriad frequencies and topologies. This is kind of a funny picture because it shows, I don't remember how many different providers on towers on the top of a hill. There's many different topologies that are needed for many different use cases, right? The permutations are exponentially higher than they've been in previous generations. And significant increase in processing is needed really to keep up with that bandwidth. Talking just a little bit about a chiplet platform for wireless. SerDes can be optimized for standards like PCIe, CXL, Ethernet, etc. But standards like CPRI and JESD, which are also very common in the wireless space, have multiple generations of silicon learning to really get them right. These are difficult interfaces. They're ever evolving interfaces. They seem to be right on top of deployment in a lot of cases. And design updates for those standards are supporting tens of gigabits per second. Memory integration is also very viable for deep buffer switching, packet processing. So this is like on module LPDDR instead of using DDR on the board, right? It gives you faster response time. It gives you a lower BER. You don't have to put ECC on it when it's closer like that, depending on your applications. And then you get significant thermal benefit as well with these multi-chip systems. You can offload the power dense pieces of your design to silicon that can handle that, to silicon that can be thermally solutioned. And those are, power density thermal solutions are key to winning in the wireless space, right? That's what the wireless customers are mostly concerned about. Think, we're going to have these base stations on top of every roof in a large city, and they're going to need to be powered through, solar power, solar energy. They're going to need to be powered off of trickle charge from the grid, et cetera. Using very little power and dissipating whatever thermal that they have in short order is going to be key to build out. In wired networking, a little of the same. Access to new technologies is just cripplingly expensive. The cost to build out the new fabs, those costs are passed on to first wafer starts. And with IP not readily available, there are significant challenges to overcome. Only the very large can generally support first in technology. But our systems, right, and customer systems have increasing cost pressures, not to mention schedule pressures. High function devices are often too much power and they cost too much, even in the low end space. So really, lower system cost memory solutions are needed, but still, right, they need the insane bandwidth and capacity that wired networking customers have always needed. Think of that. Was there a question? Sorry. Okay, apologize. So think of the challenge that the largest carrier enterprise data center customers have right now with bandwidth scaling, right? They really need switches that are required in the tens of terabits. And we're seeing customers right now, sort of the holy grail is the 50 terabit switch. That's kind of where we are. Those customers, though, still need a way to enable more chip and power effective, say 25T or even 12T switch chips, right? Derivatives, where they can no longer justify the investments in designing all three of those sets, right? They can't keep the staff on, they don't want to invest in all of the IP, 3 different tape outs, etc. So modular technology really enables the industry to offer customers the best of both worlds in those advanced technologies, without multiple designs and multiple tape outs, right? That's huge. So now you take a single piece of IP or a scalable piece of IP, and you collect it with others like it through interfacing, through a chiplet approach, ultimately through CPO, and you can scale up, scale out to your newest interfaces rather quickly. So, with modularity comes standards, and standards are absolutely essential. And that's why major investment in standardization compliance is needed. It's happening, right? Customers are pushing for it, vendors, providers are pushing for it, technology companies are pushing for it. This enables infrastructure customers to really develop solutions they can be confident will be supported over many generations. Many generations and system upgrade cycles, right? We don't want customers having to respin with completely new design points every 5 or 10 years. This is something that can scale out. You can add on, you can do midlife kickers. There's a lot of different opportunity. I think this is my last slide, but really, right, understanding infrastructure customers' challenges, especially as we go into modular building and modular platform creation. There's lots of connectivity offerings, and there's even more, right? And being able to separate your connectivity needs across technologies, your logic needs, your design needs across technologies with some of the multi-chip packaging really gives us, true scale. With that comes the need for truly open standards. OCP, I'm trying to think of some of the others and I can't off the top of my head, but there's multiple standards committees out there. And then building the best IP, the products and the technologies to put into those next generation systems. All right, the elevator pitch is over. What kind of questions and answers and discussions are people thinking?
One thing I'm disappointed, Brandon, on the deck, you don't have the dollar sign. A lot of stuff that we're doing, modularity and
Actually, yeah, you did ask. I think there's one in the backup, and I don't want to go through it live here, but yes, actually, one of the big discussions I was having with someone today. It's funny because we're solutioning a customer that has done monolithic silicon in the past. Is right, the cost. It's a great chart. The cost of packaging is going way up, right? But the cost of non-monolithic silicon is coming down, and overall, the cost of a system is becoming smaller, right? I mean, certainly if you're new, it's bigger, but it's not scaling as fast as it used to scale. And so what we're doing is we're shifting the price point away from the silicon, more into the custom packaging, so that there's an overall lower cost solution to the part. Is that the chart you're talking about, Chuck?
Yeah, I think Wolfgang just did a talk. I want to say it's a few months ago. I think one of the striking remark he left with this audience was packaging nowadays costs more than the silicon.
And it's very true, yeah. Especially when you consider, I mean, a 2.5D or a 3D chip combined with HBM. So you're talking about, multiple levels of silicon and layers of silicon on a module, or parts that have 400 discrete components on them. I mean, those packages are getting very expensive. Well over $1,000 piece prices for just laminates and packaging costs.
So if you have a client that's looking at doing this, say multi-chip approach instead of the monolith approach, how do you handle the software side of that? What does long-term support look like for drivers to ensure that all those components keep functioning into the future?
Yeah, that's a really good question. So ideally, right, these interfaces are standardized interfaces. They're either very wide, dense parallel interfaces, or they're XSR, extreme short reach SerDes like interfaces. But they become rather transparent at the software level. They don't necessarily have to be. I mean, you could certainly we certainly are engaged, at least with our standard product teams, on starting to redesign software to expect or to become aware that there are intermediate interfaces in these applications. What's nice about this, though, is you can rev your chiplets, right? I can spin these when new technology becomes available. And if I have the ability for my software, my firmware, my drivers to just come in and reconfigure my logic for some new chiplet that's attached here, I actually can scale out much quicker than I could with a respin of monolithic silicon. So there's some modularity that needs to go into your software and your firmware design as well. But I think that is in line with what software teams have been doing for a long time in scaling into the cloud. So it's not zero, right? There is certainly work to be done there. But if we're starting to go modular in our hardware design, I think it follows that certainly firmware and then ultimately software will follow that trend.
So one of the big benefit of third-party IP, the client found is that by adhering to the standard and go third-party IP, they can save a lot in terms of development, both schedule and cost. So if it's, for example, is a standard PCIe or LPDDR, those drivers are already readily available. They can just basically plug that into their existing firmware environment. So again, kind of leads back to the R&D cost and schedule. And the other thing, I mean, Brandon kind of highlight the modularity of using the chiplet. This Marvell by no means was the first one to hit the commercial success with this. The most, I would say, famous case recently was AMD. AMD was using chiplet, able to reuse some of the I don't want to say old, but less than bleeding edge technology for their IOs and analog circuit. They put those on a chiplet, and using this concept, they were able to plot those chiplet right next to their advanced silicon and able to get their server chip, out in time under the significant cost, because they don't have to remap the whole chip. They just need to remap the part that does intense computation.
I know, not just on their server chips, their Ryzen platform on desktop uses a 14 nanometer process for the IO section and a 7 nanometer for the CPU cores, which gives them a much lower cost per core of that bleeding edge technology.
It's kind of turning into their kind of Lego building block strategy. One of the article I read last week, in first quarter of 2022, I think they're releasing 53 part numbers. That is just amazing. It's like with the permutation and tailor-make solution they can have for each of the target client, how much they can do with the chiplet.
So as we're starting to see more chiplet designs get commonly used, and AMD has been shipping theirs in massive numbers for 5 years now, what are the next technological steps that will allow that to go even further? Or like, what are we currently missing that is a limitation?
I'm thinking. A limitation. Help me out, Chuck. What do you think?
How about the bandwidth?
Well, certainly yes. That's a good one. Okay, so yes. So obviously, as we start to stage the silicon out, bandwidth becomes an issue. There are new technologies being developed. I mentioned some of them in here, and I didn't get into a lot of specifics, but parallel interfaces. We've come up with a pretty unique die cut interface. This isn't a commercial, where we're getting extremely fast bandwidth. It's pretty much wire connect, right, between die. That don't really slow that down. I mean, your bottlenecks are in your XSR connections out to chiplets, things like that. And as long as those can stay at or faster than what you need for your future growth, say out in the chiplet or out in the co-packaged optics, then I think you can mitigate that. But yes, bandwidth is key. Another piece of that is playing the game with technology, right? I mean, again, jumping to 3 nanometer because there's a perceived performance benefit isn't necessarily the answer for everything. Memories don't scale, analog devices certainly don't scale. And so really, if you're logic dominated, that makes sense. But for a lot of these interfaces that depend on IP, it's really about finding the right packaging that allows you the most, let's say, real estate for that bandwidth. And I think that's where the heavy cost of packaging starts to come in.
When you say packaging, Brandon, that's just general first level packaging and second level packaging, or is it something different than?
No,
than
it's.
that?
I mean, take for instance this this cheesy little cartoon I've got on the screen, but this is really this is really like a single module. Ultimately, this could even be something on an interposer, right? And so we're talking about not only multi-chip modules, but we're talking about 2.5D and 3D scaling, where the cost to integrate multiple silicon units in a, I don't want to say on a laminate because I could mean on an interposer, in that unit is going to increase. Each piece of silicon is rather small, right? It seems sort of like a departure from SoC, if you will, where we were in a hurry to put everything onto one piece of silicon, right? It's really deconstructing the monolithic silicon, but with that comes that increased cost of packaging. So yes to all. Level 1, right? Bumps, what's the word I'm looking for? Bond and assembly. But also, when you start to sneak in interposer, if you do have 3D, right, we're looking at 3D stacked memories, things like that. And then co-packaged optics. I think that's the next big one for us.
And you had mentioned that some of the customers or most of your customers are pretty sophisticated, right? So do you find that the customers have quite a bit of capability on that package level design, or does it kind of vary by client?
Yeah, I mean, that to some extent that becomes a service as well. So customers aren't necessarily doing the packaging. what we are finding is that the OSATs, the outsourced packaging providers, are becoming much more sophisticated. The fab houses, TSMC, we know TSMC, they're becoming much more sophisticated in their CoWoS offering. Customers are coming to us saying, we expect this will be chiplet based, right? Customers are coming to us asking us to make modular chiplets that are not only going to be good for them, but will be standardized and can be offered as a standard product. So it's very, I would say from our customer base, it's extremely common to see customers already thinking this way. So they're already down the path of modularity. Especially some of the establishment customers like wired networking, right? That have played for years in waiting for that next node, and their only benefit has been the Moore's law scaling to sneak more function and ergo power into their designs. So by being able to offload 224 gig SerDes or 112 gig SerDes, by being able to offload CPO, focus instead on their custom logic block, and then put a standardized interface out to chiplets, that sort of alleviates them of the immediate need to design a chip in 6 months and get it out the door. They know there'll be a chiplet out there that they can attach to, and when the optics catch up, they can rev it without revving their ASIC.
See, okay, thanks.
And just one comment about the TSMC and its packaging drive. So TSMC is now recognized that the packaging is becoming the limiting factor to adoption of its technology and wafer cell. So since the fourth quarter of last year, they have been very proactive at enabling the OSAT to take advantage of their CoWoS technology. So more and more we see that the customer choose the foundry because of the packaging enablement that tie with that specific technology. And again, it kind of goes back to people are trying to differentiate their application using whatever they can. Package is definitely one thing that they are working on right now.
Yeah, I think we single-handedly drove a resource increase in TSMC's CoWoS offering, which is really good.
Yep.
They're getting the message finally too, that this is how they're going to fill their fab with some very large customers.
Interesting.
TSMC is always kind of worried about being caught up, right? And Samsung is definitely doing great in terms of the Gate-All-Around and other initiative. So, that's the great thing about having competition. The two were always trying to leapfrog each other.
Yeah, HBM was a great case in that. Sorry, Bob, go ahead.
I've got a question, Brandon. You said you were talking about standards being pretty much essential to cost and
yeah, and I know who I'm talking to when I say that, the IEEE, but yeah.
Yeah, that's what I was going to ask. Is a lot of these standards IEEE, are they coming from other areas, or where are the standards being set?
Yeah, it's a good question. There's an OCP group that's effectively standard. That's what is OCP? It's not just on chip packaging. I'm trying to remember what that is. Somebody will look that one up for me. There's a couple different, there's a number of different, what do I want to call it? Package standardization companies, right? Or companies. Let me start over. Package standards that are starting to emerge. There are interface standards, JESD, IEEE, how we test chiplets, right? CPRI standards, things like that for wireless. And I think that these start as consortiums, and then they start to grow and build. I don't know how many of them are what I would call completely locked down standards, as much as they're heavily followed and heavily attended work groups. But yeah, did you write one down here for me, Chuck?
Yeah, so kind of along with that, some of the biggest pushers, surprisingly, is from the cloud behemoths themselves, because standardization and openness allow them to integrate multiple solutions onto existing offering, and in the process, driving the schedule and cost of doing new development low. So Facebook for the last, was this even back in 2012, they have been very vocal about the open server initiative, right? So they try to drive the openness into how to do the server design. And in the last 5 years, they're trying to push that into the silicon design realm.
Yeah, open compute. That's what I was trying to come up with. I couldn't get there, but the open compute project, right? So this is being driven by all the FANGs, right? A lot of the large network customers.
System players.
The system players as a standard approach to modular design for hardware.
These guys, I mean, they have been very, very vocal since 2010, 2012 that no longer they want to buy servers. They want to make their own server because they want to drive down the cost themselves, and they just want to build the system that's good enough for their application.
Yeah, I mean, we don't talk to them if we don't speak OCP. If we're not participating in the OCP panels, that's kind of a non-starter for some of these emerging plays.
Yep.
Hey, Brandon. Scott Free here. How are you?
Hey, Scott. Good. How are you?
Good, good. Hey, can you sing a few bars about kind of power and power dissipation and how you do this in this modular world? I mean, if you're pulling something off, replacing it, and you stick more silicon in than you can cool, I mean, what's going on with that?
Yeah, that's a good point. And actually, one of the points I was just talking to Aiden about, let me see if I can find, I had a slide here. Because one of the places we see that, I mean, it happens in every space, but one of the places we see it really being a crunch point is in wireless, right? Certainly the 5G companies, where the power density of these parts is really sort of the gateway to entry, right? Or I should say the barrier to entry. So by offloading function from monolithic silicon, we can actually start to distribute the power density around. Yes, it's more silicon, but you have these more custom blocks of silicon, which are modular, right? You can scale them. And now you can talk about thermal solutions in different parts of that module or that package. And so it gives you some play there to accomplish, right, both the power density and thermal solutioning.
And you kind of still resort to your old bag of tricks, trying to do frequency scaling, voltage island, the header.
Oh yeah,
all that kind of stuff.
Yeah, all the normal plays that we've done, right? We used to, we've done process-based voltage compensation. We have adaptive voltage scaling techniques now. Again, incredibly useful in the wireless market. This is right. Where you've got a baseband or a radio chip sitting out there, and 99.9% of the time it's not doing anything. Yeah. And you want that sucker shut down and running low and not dissipating anything. And so by evaluating the workload over a time function, right, you're not really looking at instantaneous power. That does become a problem when traffic rates are high, but you can now start to solve this thing more in a time domain. But those aren't terribly new tricks, right? We've experimented with things like that for years.
Yeah, but it's kind of interesting that some of the tricks that we pull on the processor now is kind of getting to ASIC.
Well, yeah, I mean, it's all of the high end. You're trying to squeeze everything you can out of silicon. We've never had to do this before because every 18 months we got a new node that did everything for us. So nobody ever had to think twice. The hardware guys revved, the software could never keep up, and life was good. Yep. But now we have to squeeze more out of the silicon. Silicon's not dead. I don't think that silicon's going to go anywhere for a long time. We're just finally opening up that new frontier of moving away from monolithic more towards modular design. And so I'm not pretending that there aren't power density issues, right? By moving my incredibly sophisticated logic design to an N3 chip while I leave all of my communications on an N5 chip now makes that guy even hotter. And because I'm getting the density and the logic in that thing, I have a new problem to solve. Now I'm starting to have these little pieces of silicon with hotspots, and I have to be very creative about how to solve those.
Mm-hmm.
Hi, Brandon. Thanks for presenting. Appreciate it.
Hey, Dave.
I remember touching on a little of stuff, probably more from the patenting angle, if I recall. And one of the issues that always came up was the overhead required for testing in ESD. When you start breaking your chip apart, right? You end up with those two big problems.
Do I have a PhD for you to talk to, Dave?
Have there? Well, we'll start off here. Well, anyway, have there been any recent advancements to address those two issues?
I would say that is emerging field. Yeah, I mean, to be clear, right? This is emerging technology, right? We do have chiplets. We've done chiplets on test sites. Those are coming out. We're starting to look at a lot more of the 2.5D, the 3D, the multi-chip module integration. But I think there's a lot of discovery to be had there. Yes, we're thinking about it. Yes, we're looking at it. Yes, power grid integrity across multiple pieces of silicon, package losses, interference, ESD. My gosh, the ESD requirements for some of the newer technologies are incredibly tight, right? So even into fabrication and bond and assembly, putting these things together is incredibly difficult, especially when you're offshoring that to OSATs that you're teaching this stuff to. So there's a lot of knowledge to be gained there. I think we're aware of it. We're in awareness mode. We're in holy cow, we have an engineering challenge to overcome here. And I think that one place that I have seen a lot of improvement is in some of the packaging tools. They're starting to become much more aware of the multi-die packaging stuff. And so I think a lot of the advancements we've seen into like place and route tools over the last 10 to 15 years, we're going to now start seeing morph into more of the packaging tools that have, I think, kind of largely been left in the dust.
Likewise with the PSI tool, right? The volts right now, the Cadence has made a lot of improvement in the last 5 years.
Yeah, and that's for silicon measuring, right? And so now we're talking about, what's the next step? Well, it's to take technologies like that and migrate them into the package space,
right?
And then into the board space, right? S parameters may not be enough anymore. We have to do, full dynamic simulations. Okay, bring it on.
It's definitely something that keep the ASIC team, worried at night, especially that versus your traditional component play where you can learn this kind of stuff evolutionary. I mean, step by step. So you push out a product, okay, based on the learning from it, you push out a better next generation product. In a way, ASIC, you got to do it the first time right. And how do you achieve that first time right? It's kind of like black magic.
Well, when you run an entire business model off of it, yeah, that first time right is important.
Yeah.
From an engineering challenge, it's certainly fun, but yeah, now you throw into it the need of first time right. You're right.
Yep. Paul and Dave.
Any other questions for Brandon? Just one kind of specific question, Brandon. You mentioned some of the standards, and you mentioned JESD in particular, but are there a bunch of those types of things, SerDes interface type standards that you run into over and over? Or is it just a real finite set, would
Well,
you say?
I think yes, and I'm certainly not an expert on all of them, to be fair. But there's also, consider it's not just the logic and the integration standards, it's the test standards, right? It's the test design standards, it's the how are you going to bring this thing up? How are you going to perform rat back tests on third-party IP? So there's a lot that, end to end, there's a lot of opportunity to standardize some of these so that, so that I think multiple players in the industry can participate. So, how are you, let me try to think of some, I'm struggling off the top of my head here. I was going to get into design for tests, but I think that's a different day. Yeah, so I think that there are opportunities to further standardize. I don't know how much of this has been robustly established yet. Certainly the calls to action by the very large providers are pushing us in that direction, right? Like I mentioned with OCP and with some of the others. But I think out of those will come, I'm hoping out of those will come, more rigorous standards for interface specs.
Yeah, okay. Any other questions from anyone?
Hey, Brandon, this is Brian. How you doing?
Hey, Brian. Good. How are you, man?
Long time no talk.
Yeah.
I got a question for you guys. What are y'all seeing in terms of any FPGA type activity with this stuff? Is it all still pure ASIC? Is any FPGA modules, or is that play a function in any of the things that you're seeing these days?
Well, so I'll give you my perspective, and it's funny because I've got the wireless thing up here, but the ever-evolving CPRI and JESD standards have forced a lot of the wireless customers to develop almost up to the point of productization FPGA solutions. And in fact, some of the very large wireless providers are shipping FPGA-based solutions because they're shipping before standards are set. I think that okay. So on another end, we're seeing a lot of interest moving towards embedded FPGA. There's a lot of embedded FPGA companies out there. I think that function that isn't quite ready for prime time, things where standards are still evolving, are starting to look at embedded FPGA. These are FPGAs that go into your ASIC, right? Embedded FPGA to solution those standards to provide a place for firmware updates, etc., on some of these interfaces, so that my ASIC, my custom logic design, can continue and tape out and productize. So absolutely yes. How much of the FPGA content will be long-term is unclear. I think as long as things are shifting and requirements are unclear, you'll see a need for FPGA because, as the name indicates, they can be field reprogrammed. We can do that with ROMs. We can do that with other on-chip capacity too. We can do it with, we've done it through CPU subsystems, things like that. But I do think there's a play there, and I think that they one thing that comes to mind too is co-package optics, right? As we start to look at 200 gig, 224 gig SerDes, copper's gone, right? I mean, you're fully optic, and there's going to be a ton of learning and industry tap dancing to get those interfaces to work. And I think that's a place where I expect to see the embedded FPGA market start to make a play. That's, whether that's on the chiplet, whether that's on the base ASIC is unclear yet. But I think that that's a place where we'll see some movement.
All right, any other questions for Brandon? All right, well, thank you so much, Brandon. Thank you, Chuck, for your help as well in getting this set up and sent out. I appreciate everybody's attendance this evening. We're trying to get our next meeting set for next month. I don't know that we have that quite nailed down yet, but we're getting there. So watch for communications from IEEE of Southern Minnesota for that. Any other comments for tonight?
Thanks for having me, Paul. Appreciate it.
Yes, thank you so much. And we generally give our speakers, Brandon, a IEEE mug. So we'll try, or I guess it's a tumbler now. So we'll try and find a way to get that to you, probably through Chuck, since he's on the board. But
good, because my Global Foundries one is getting kind of old in the tooth here. So.
Good, and timing's perfect.
I'd rather tote some IEEE stuff.
Yeah, we've got about 45 of them left, so we need to get you one. So
if anybody wants some Global Foundries plastic cups, let me know. We've got a billion of them.